didn't understand any of the verbiage. Right? This was grid computing for me for many years. I heard a lot of people say things about grids that I, as a builder of many, many grids, couldn't understand. And I got really nervous because you started to see just a great deal of commercial interest in this, unlike when we were doing the grid, where it was chemists and physicists and biologists and other propeller heads. These were people who are the captains of industry. And so this is a smattering of the things that that came up. And what I'll point out is that on April 14th of 2008, if you type cloud computing into Google, you get 527,000 hits. Now, I did that this morning in my hotel room, and it's 20 million. Right? That's not. It's just going on a year, a little bit longer than a year. That's the response. To give you some context, because numbers without context are often confusing, Barack Obama is 105 million. So it's, not quite Barack Obama, but credit default swap is about 1.7 million. Right? These are things that are important to our society, and so you can get some idea of how important, presumably. The takeaway message here, though, is that if Sergey Brin is to be believed and Google is the mind of God, God's thinking about cloud computing, and so we too should be thinking about cloud computing. These are other people, not God, thinking about cloud computing. These are investors, right? This is a montage of just a small smattering of the. Smattering's large? No, sorry. Anyway, small smattering of the companies that are producing something in cloud space, right? Some of them are huge companies. The investments are gigantic. Some of them are very, very small startup companies. But what we were seeing is not only is there a lot of verbiage that we didn't understand, there's a lot of money that people are putting into this paradigm. And we really wanted to understand it, right? We really wanted to understand what it was that we all should be thinking about along with God and investing our money in. Okay, so now what I'm going to do is try and provide a little bit of what it is that we believe they were thinking about. And this is controversial. I know it doesn't look controversial, but this is a very, very controversial slide, because if you go to a cloud meeting, what you will find is that a number of cloud potentates, people who are the CTOs of very large cloud companies, will tell you they will not define a cloud for you, right? I find that disturbing. The reason they won't define a cloud for you is because they're afraid to be locked into the term. Lock-in is a big fear in cloud space. And it's so much of a fear that we won't even say what a cloud is without being afraid of being locked into that definition. I have no such fear. I will tell you what it is people mean when they say cloud computing today. Now, this is not what they may mean in a week, but right now, this is what they mean. It starts out with the notion that there are organizations, companies, that have very, very large data centers. And those data centers, this is Google's Columbia River Gorge data center, we think. And just to give you some idea of scale, that's 100 meters by 50 meters by 4 stories. So these data centers are chock full of resources. And those resources are there ostensibly handle whatever it is that this company does normally. But along about 2004, Amazon.com figured out that through virtualization technologies, they could start renting space in their data centers. And the key realization here is that their infrastructure for selling you things, like CDs and DVDs and camcorders and all the things that you can buy from Amazon, including books, it could be used in the same way, the same e-commerce style, to rent you space. Right? They have all the tooling necessary to pull this off. And all they needed was virtualization and some scalable technology so that the e-commerce infrastructure, the rental space, scales. Great. If that's the case, then really what's sitting in between what it is you're renting and your users are web services, right? Because that's what Amazon builds its venues out of. When you go to an Amazon.com splash page the first time, before you've logged in, there are 200 different web servers that are producing content for that one page. 200. Right? That is a multi-tenant, if you will, service application, and it's all web service technology, right, at some level. Okay, so we're going to have web services and we're going to rent out space. And the missing piece, the piece that's a computer science innovation from a distributed systems perspective, is that the customers of this cannot interact with a human being when they do this rental, right? If every time you bought a camcorder you had to talk to somebody, Amazon's camcorder business would not scale with the number of users, number of customers that they service. That's true for this rental market. You need for your users to be able to do this rental completely automatically. In order for that to happen, there needs to be a description of what it is they're renting. Amazon calls this an SLA. I don't know if they do, but everybody else calls this an SLA. It's not an SLA. An SLA is a statistical description typically of a one-dimensional parameter associated with a resource. This is really a quality of service specification, but in business terms, we like the term SLA. So think QoS specification when you see the word SLA in this space. And that's just necessary so that your users can rent without talking to anybody about what it is they're renting. So that's a cloud, right? That is the definition of a public cloud. We're starting to qualify. That's fine. And really what it is it's large-scale infrastructure for rent, fully customer self-service, SLA described, and an e-commerce transaction. That's very important. It is an e-commerce transaction. You're going to make a request, like you do for a DVD, and either that request is satisfied or it's not. You don't get half a DVD. You don't get something that says, oh, gee, I'm going to give you the first half of Mary Poppins, and maybe I'll give you a refund because the DVD you got only has the first half of Mary Poppins on it. Either you buy the DVD or you don't. It's transactional. That's the model for the public cloud. And it is nothing else, right? Okay, so if that's the model, and you're a computer science researcher like I am, you have a lot of questions immediately. And the first question is actually one that came out of my grid experience. What we found over many years, and I see many of my grid colleagues in the audience, and they can either verify or refute this, is that there are a number of things that run really, really well in a grid, and a lot of things that don't. Right? It's not a one-size-fits-all computational model. In fact, nothing really is, but we are painfully aware of that in grid space because there are just certain application classes or styles or whatever that seem to be well suited to the federated and heterogeneous nature of grids, and other things just don't work very well in that environment. They're too complicated, they're too failure-prone, whatever. Clouds are likely to be the same way. We know of an application class that runs really well in a cloud. That's web service hosting. Right? It's clearly the case that small and medium businesses can build websites very quickly inside a cloud. Is that it? What applications, in addition to small websites, do clouds run well? And at the time we did this, there was no way to figure this out. If you went to ask Amazon, or you try to run an Amazon, you got a lot of web service hosting and very little else. And the other thing that we noticed is that there are a lot of features of cloud computing that are not e-commerce based, that are very attractive to other constituencies. For example, at UC Santa Barbara, the IT staff, who reported to me as their facilities chair, really loved the idea of legacy support. The idea that a professor, like myself, who wanted to use a piece of software that was 15 years old, could encapsulate that into a VM image, and when that professor taught his class or her class every spring, let's say, those images could be trotted out and given to the students and then put away, and the IT staff never had to be involved. That's not an e-commerce transaction, right? There's no credit card, there's no refund policy, there's no complaint department, thank heavens, so on and so forth, but it's a feature of the cloud. So could that be done in clouds for on-premise use? Can't do that with Amazon. And then lastly, there are a number of technological innovations that are coming down the pipe, we believe, that clouds are not well suited to, even very, very sophisticated clouds like Google. And the one that I'll give you an example of is data assimilation. We're actually working on this at UCSB. The question here is one that's really posed by David Culler and his SensorNet colleagues, and it goes like this. In the future, the not too distant future, say the next 10 years, everything you own is going to have some kind of sensor in it. Everything. Your wristwatch, your milk, your refrigerator, your pets, your children. And those sensors are going to be trying to tell you something all the time. Right? Now, the things about sensors to understand is they don't all speak the same language. They don't all speak at the same time. They speak in different periodicities. There's different accuracy in what they say. You have to try to make sense out of that. You have to infer. It's called an inference. You have to make an inference out of this constantly multidimensional streaming data. How are you going to do that processing? Well, it's not going to be through Google. right? Google's model is completely backwards for this problem. Google's model is an asynchronous data acquisition model. When you get a web page, when Google crawls the web, the page could be 3 weeks old or 30 seconds old, and when you query, it's all presented to you as if it happened right now. They synchronize in time the query. They do not synchronize in time the ingress. In the data assimilation case, it's completely the opposite. You're doing way more updates than you're doing fetches, and all the stuff has to be time correlated. It's not a Google Cloud. So if you think, wow, Google's going to solve this problem with their existing infrastructure, they're not. How are you going to solve this problem? We don't know. It's a great computer science question. Same thing is true for multiplayer gaming. We hypothesized that this was a problem that you couldn't solve in the public clouds. It turns out to be true. A lot of our users are trying to build multiplayer games out of Eucalyptus. And we think of Eucalyptus itself as being a multiplayer game, but that's another matter. And then mobile devices. Cell phones have a lot to tell everybody about what their owners are doing. You increasingly use your cell phone for more than just making phone calls. And when you do, you are providing valuable information either to you or to someone who wants to sell you something. And this is really just kind of a coarser-grained version of the data assimilation problem, perhaps with a little bit more emphasis on localization. So these are all disciplines that cloud computing, dynamic provisioning, multi-tenancy, self-service could really help, but there was no way to investigate these things, at least as a university researcher, that I could see. And the reason is because in order for me to research something at the systems level, I really need an infrastructure. And in particular, since I work at a university, a public university, I need an open source infrastructure, one that's free and one that I get source code to, right? So I told my group, okay, group, your job is to go out and find me an open source infrastructure. I'll be in my office. And they said, well, what should this look like? And I said, well, it's got to be simple. This can't be something that is so complicated that once we get it running, we can't see inside it, we can't instrument it, we don't understand what it's doing, right? Arguably, some of the grid technologies that we and other people have developed do not possess this property. Secondly, it has to be extensible. If I'm going to do this research and I've got the source code, I need to be able to add things to the source code. I need to be able to change things in the source code. I need to be able to reconfigure what it is to do the data assimilation cloud or the multiplayer gaming cloud or whatever cloud it is that I wish to do. It has to be commodity-based. This is very, very important in the university environment. I do a lot of grid research, and I go to the IT staff who work for me at UCSB, and I say, here, you need to clean off the operating systems on all of your machines so I can install this grid package at that version of the operating system. And they say, vaya con Dios. Absolutely not. What happens when you're out of town? My people are not trained to do this. We're not paid enough to destabilize the environment just so that you can do your research. Go away. So basically what this says is that the extent software, in addition to the extant hardware, has to be considered infrastructure. You need to be able to lay this on top of whatever's there, and I mean whatever's there, 5-year-old Linux, last week's Dell hardware, whatever it is, in order to be able to get people to get value out of this, at least as a research tool. And lastly, it has to be easy, and this is again a grid lesson. Grid systems work really, really well for their users once they're installed. But it can take a year. I am not exaggerating, and Shava's laughing. I see her laugh because she's probably spent that year trying to get grid systems to work in an environment that has users. Meanwhile, if you don't have Shava, your system administrators who are facing the burden of trying to get this to work become your enemies. They will do everything in their power to remove your software from their system. They will convince their bosses that your users should never see this software unless it's easy to install and easy to maintain. We know this firsthand, and so we said, whatever the cloud, open source cloud infrastructure is, it better be that. And so they went off, and they thought about that, and they came back and they said, Rich, geez, there's really not a lot out there. And I made them go back like 3 or 4 times because I didn't believe them. And sure enough, as near as we could tell, there's just not a lot out there that does cloud computing in open source. The Globus project, many of you are familiar with the Globus project. They actually have a cloud component. It's called Nimbus. It's all GT4 based, right? They've got WSRF wrapped around it. This is a lot of grid web service talk. The important thing to understand about this is that it's really Globus. And Globus, while it is a fabulous grid technology, doesn't possess all of those properties that we would need. It's fairly opaque. It's difficult to modify. I'll let Shava tell you about how hard it is to install and maintain. And so it really wasn't going to meet our needs as a cloud computing And really, Globus, Nimbus is qualified to answer another question, which is, if you took grid technologies and you tried to make them behave like a cloud, what would happen? And we really wanted to know something about cloud computing, not grid computing behaving like cloud computing. So that wasn't going to do it. There is an open source Java-based technology called the ECP. It was formerly called Anomalism. It's by a company called Anomaly in Toronto. It's REST-based, so it doesn't support the SOAP bindings that EC2 does. That's one issue. But the bigger issue is it's a plugin architecture. And plugin architectures have strong points and weak points. The strong points are that you can easily replace things. That's obvious. The weak points are that if you need to plug something in that's really coordinated across multiple services, it's very hard to do that coordination, right? So for example, in the cloud, we have to really focus on network provisioning. And it's hard to do network isolation as a plugin because you need several plugins. And if they're not at the right rev level and are not talking to each other with the right set of certificates, it's going to break. And so their model, this plugin thing, it works well for some things, but it doesn't work well for others. So we really couldn't use it. And lastly, there's a European project called Reservoir. And the reason I put this up there is because there's a subcomponent of Reservoir called Open Nebula. Open Nebula is a virtualization control technology. You can think of this as a very, very lovely set of Python bindings to the Zen virtualization control mechanisms. That is not cloud computing. And the reason it's not cloud computing is because there are no SLAs. Right? And it's not user provision. There's a system administrator who's doing all the control. But Reservoir itself has as a mandate the verbiage in a lot of what they produce that talks about cloud computing. And at some point they will, I believe, produce cloud software. It's just at the time we were doing this, there really wasn't any software we could call upon, just a lot of really good documentation. So in the absence of something that we could steal, we had to build. And what we built was Eucalyptus. And people ask all the time, how did it get its name? And the answer is that at UC Santa Barbara, for reasons that escape me, there are many, many eucalyptus trees. There are a few palm trees, but many eucalyptus trees. So my fabulous group came back and said, we want to call it eucalyptus. And I said, OK, but what does it stand for? And they're like, no, that's what it stands for. Elastic Utility Computing Architecture, linking your program to useful systems. Now you see the contribution that I have made to the project. It is web service-based elastic computing infrastructure, where the web service technology is available from a common Linux distribution. That was the mandate. You can't go get some weirdo web service thing that's half proprietary. You can't invent some bizarre plugin architecture. It's got to be Tomcat. It's got to be Apache. You've got to get it from all the Linux distributions, and that's what it is. It hosts Linux images. That's what Amazon was doing. Amazon at the time did not have Windows support when we started this. That shows you how fast this stuff rolls forward, because we released May 28th of last year. And in that time, Amazon released Windows support. But at the time, it was just Linux. And we were faced immediately with this question of, well, Rich, you were just criticizing the Globus people for grid technologies and calling them a cloud. How do we know what you've built is a cloud? And I tried, unsuccessfully, to argue that. I tried putting together all of these, what I thought of as beautiful, cogent arguments for why what we were doing was cloud computing, and they were all shouted down. And so we said, OK, we're going to not have that debate, since it doesn't seem all that productive. Instead, what we're going to do is identify something that everybody agrees is a cloud, and then demonstrate that our software is indistinguishable from that in terms of the APIs it supports. At the time, the only answer was Amazon.com. So we said, OK, Turing test. We are going to build something, and we're going to pretend to be Amazon. And if your thing can not tell the difference between us and Amazon, we win. If it can, we've made a mistake. That's a wonderful engineering technique, by the way, because you know who's wrong. There's no arguing about users. There's no arguing about style. There's no arguing about what's coming. Either it does what Amazon says it should do or not. And we've tested this with both users and services that are targeting Amazon. And that was a really good focusing tool. The important thing to understand, though, is that we didn't want to build Amazon, and we didn't even want to build something that was only Amazon. So the Amazonian parts of Eucalyptus are confined to a single set of modules. It's really an open source infrastructure for building clouds in the back end with an Amazon interface module, and we're actually building other interface modules that can coexist with it today. It has this overlay property. You can drop it onto your existing installation, and if your existing installation supports virtualization, either Zen or KVM in open source, course, but it doesn't matter really which versions, too much. You can get yourself a Eucalyptus cloud. You might not get all the features. If you don't allow us to do things like modify your IP tables, you won't get security groups, but there's a feature to intrusiveness mapping that is explicit in Eucalyptus, so your system administrators can let you start out with a baby version, and then as they gain trust, either with the software or with you, allow you more and more access. And installation and maintenance are constantly improving, but something we really focused on early on because contrary to what you might think, your system administrators actually are people. So what are the goals? The goals were certainly to foster research. We wanted people to have, like us, at their disposal, an infrastructure that would allow them in a very empirical way to experiment with cloud computing. Not data center virtualization, not grid computing, not web service hosting or container-based stuff, cloud computing, demonstrable cloud computing. And that is what we were intending to do. It actually turns out, though, that very early on in the project, a bunch of other usages emerged. The scientists at UCSB, when they heard about this, began downloading Eucalyptus and calling us on the phone frantically and saying, look, I really want to know whether my application will work well in Amazon.com. I don't want to spend the money on Amazon. I don't really understand how Amazon works. I got your source code. Let me use Eucalyptus as a development platform. Let me build the images I want, or download the images from Amazon and experiment with them, or figure out whether S3, which is this eventually consistent storage model that Amazon supports, that we support as well, let me see if that's going to work for my application. And so you have this development notion that emerged very, very quickly as something that people were interested in. And later on, and something that we're seeing now, is really there's this ability to be able to couple Amazon with your local data center using Eucalyptus. You might want to do that for development purposes. You might want to do that because the data that you want to compute over, you're just not comfortable with putting up into a big public cloud where you can't really keep track of who can see it and whether it's going to be available to you, this kind of thing. And so this homogenization of your local infrastructure and public clouds, we think is very important. It's something that lots of people use it for, and this actually has some bearing on what we think the future looks like. What it's not, though, is it's not a replacement for Amazon.com. And I say this, I mean, nobody in this room, I'm sure, believes that, but you'd be surprised as to how many eager entrepreneurs write to us and say, thank you for doing this. I'm downloading your software, and I'm going to go off and compete with Amazon.com. Could I please have the credit card modules? And I'm thinking, you cannot download Amazon.com in a tarball. You can't, right? It's not going to happen. First off, I would be willing to bet, I don't know, but I would be willing to wager that about 10% of Amazon.com is software. They have personnel, they have replacement policies, they have bandwidth contracts, they have failover mechanisms, they have all of this other stuff that enables them to run an e-commerce site on a planetary level. That's not downloadable, right? The golf carts you need to run people around their data centers to replace failed hardware, you can't download those in a tarball. So people have just got to get over this, right? This is not a replacement for Amazon.com. It works at a smaller scale. Yes, it does work at a data center scale. You can run it on a fairly large cluster. Amazon is more than one fairly large cluster in more than one place. Okay, so there's your disclaimer. Right, so now, if you're going to do this, and I guess we have, but if I had known, I probably would have done something else with my life, you need to solve a bunch of problems, and they're all thorny. The first one is you need to be able to build something that is extensible. And we all think of ourselves as really good extensible systems designers. The key that we thought to use this time, as opposed to the other times we thought of ourselves as extensible systems designers, was simplicity. If you look at Amazon, what those guys and gals did very, very carefully was they recognized that simple scales. And so they very, very carefully, in our estimation, focused on making as much of the internal architecture and the functionality that exports simple as a way of getting stability at scale. And that also gives you extensibility. If you start with something simple, you can add things that are complex. But if you start with something complex, adding more complexity is often difficult. Second problem we had to solve was the interface problem. We are terrible interface designers. I know this empirically. And so we decided we're just not going to design interfaces. We're going to basically mimic whatever cloud interfaces people want us to mimic until such time we believe we know enough about how clouds should operate for a particular application class, and then we might try our own interface. We haven't done it yet. I'm beginning to think we might have some inklings on what to do there. So for the moment, it's AWS, and then I'll tell you a little bit later about Google. You have to solve a compute, network, and storage problem. Virtualization solves the compute problem for you. It gives you memory and CPUs in a virtualized container. Hypervisors don't know anything about other hypervisors. And so if you're going to take a bunch of hypervisors and you're going to put them in a collection and then attach some sort of security policy to the collection, you need to have a networking layer, and that's not part of the hypervisor. You have to roll that yourself, and then add storage to that. And there's really two storage abstractions for Amazon. There's S3 and the Elastic Block Store, and both of those have to be part of the collection. They have to be authenticated. They have to be protected. All the security groups and mechanisms have to work, and they have to be isolated. You have to do all those things atomically, right? It's transactional. I need storage, network, and compute all together, or I need none of it. Those are the semantics, and so you have to basically put that together. You're not going to get that from Zen. Security, absolutely, there are security issues, and what we decided to do was essentially focus on the inter-service security. Eucalyptus is organized as a bunch of cooperating services, and we use WS Security, the W3 standard, to allow those processes in those services to authenticate themselves to each other. This is not enough security, right? Now the message traffic is not encrypted, so on and so forth, but for an academic environment, first cut, it seems to have worked. You can't really spoof a Eucalyptus process easily. I hope Stefan Savage is not in the audience. And then the packaging, installation, and maintenance issue. And here, the challenge is you're building something that emulates what is designed for a very specific infrastructure, for a known collection of hardware and software components. But you're building it so that anybody with whatever they've got can run it. There are people who run Eucalyptus on their iPhone. Right? It has to be that portable if it's going to be open source. Contrast that with Amazon. Amazon's not portable to anything. So you have this minimal intrusiveness while achieving maximal portability problem, and that's really a coding practice issue which we developed back in the grid days. Here's the architecture. I promised you it was simple. Basically, there's a client-side API translator, and for Amazon that speaks REST up the top, and it also speaks SOAP. Amazon supports both SOAP, bindings described by WSDL, and REST. And then essentially the system bifurcates. The virtualization, VM control stuff comes through something called the cloud controller. And for historical reasons, at the moment, the cloud controller also manages the credentials database. Cloud Controller uses two components to actually control how virtual machines are allocated, deallocated, and authenticated. There's a cluster controller, and the cluster controller controls all of the resources, IP addresses, memories, and nodes within a particular cluster, and then a node controller at the very bottom that actually does the actuation of the VM commands. One of the problems you have to solve if you're not Amazon is the sparse IP problem. Amazon.com has an infinite supply of IP addresses. Most universities don't. So when I get a cluster, I get one externally routable IP address, but a lot of internally routable ones behind a NAT. And if you want to combine clusters, you basically have to be able to do the network provisioning through a layer 3 tunnel that goes out through your head nodes. And so that's really helpful to have some sort of proxy sitting on the front end. It also does two-level resource allocation. The cluster controllers know what the individual nodes are doing, but we didn't want to centralize that knowledge in the cloud controller because it limits scale. So the cloud controller only understands capacity in the various clusters, not what VMs are actually running where. And there's a bit of a consistency question that you have to solve. On the other side of the screen is the storage stack, Walrus, and it was a very late night when we named it Walrus. It's really the S3 emulation, and this is just eventually consistent put-get semantics drilled down through the node controller, so all the authentication stuff works. If you're going to do Amazon's image management stuff, and you have to if you want to do the compatibility, you must do this very, very carefully, and that's because Amazon uses an encrypted version of, uses Walrus and encryption to store its machine images, and they're signed, so that you know a machine image you're running inside Amazon is in fact secure. You have to emulate all of that perfectly if you want to move images back and forth, and so Walrus actually understands an awful lot about the credentials management mechanisms and about encryption technology that's laced through the system. And then there's a piece that's missing, and I just didn't know how to put it up there. The Elastic Block Store is a network-attached storage mechanism, but not one that you normally associate with that term. It's actually injecting disk block commands into the Ethernet frames. Amazon supports this. They only support it within what's called a single availability zone, which is a single area where layer 2 provisioning is supported. We actually support it across through tunneling, but the elastic block store stuff essentially runs at the head node of each cluster. So it's simple. The other part of this is we use SOAP and SOAP bindings for everything so that there's WSDL, machine-readable specifications for every line you see on that graph. If you wish to replace a component, the API is documented in a machine-readable way. You can generate the stubs for the components from the WSDL. And we found that was to be very important for extensibility reasons. Client-side interface, EC2, S3, EBS. We use availability zones to represent essentially clusters. Availability zones are like data centers in Amazon. We're scaled down. Both interfaces. New APIs. Sun has announced a public cloud, and they asked us to take a look at their API very early on, both to give them some feedback and also to answer the question whether we could support it. The answer is yes. We are currently working on it. I don't know when it will be delivered, but it's a good test for us for multiple APIs. We've actually prototyped 2 or 3 of them. This one I think will be the first one we roll. And system administration is really different. While Amazon tells you a lot in its documentation about what the client sees, it tells you nothing about what a cloud administrator sees. So we have to make this up. We've basically built a whole bunch of system administration tools for the cloud, and that's been an interesting exercise as well. If you're going to do networking, you have some real problems, and that's because changing the networking in an installation is very intrusive. And so we really support 3 modes. The mode that everybody is most comfortable with when they start is system mode. When Eucalyptus boots up in system mode, it just queries the local DHCP server for IP addresses. Whatever it gets back, it uses. You think this is a good idea until you fire up 100 VMs and it soaks up all the IP addresses on your DHCP server. Then you're a little less pleased. If you switch, you allow us to do IP management, then we run a DHCP server locally. Eucalyptus talks to that, and we'll only hand out the IPs that you want, but then you have to allow us essentially to run a DHCP server in your environment, and some people are very nervous about that. But then the last mode, which is manage mode, we add to that IP allocation mechanism, VLANs, dynamically allocated VLANs. You actually get network isolation as well as elastic IP addresses and security groups. But to pull that off, we have to be able to modify the IP tables in your system, and it has to be VLAN clean. And so a lot of installations are very, very nervous about letting you touch their IP tables because they're implementing security policies in IP tables. So beware, but it's there. Right, and so let's see, enough of networking. Security, WS security. The one thing I'll point out here is that we just stole the e-commerce sign-up mechanism. If you stand up a Eucalyptus cloud, the person who's doing the install becomes the cloud administrator. They can issue credentials. It's done through a web page, so when someone requests credentials, an email gets sent, and you can either approve or deny. There's just that simple mechanism there. It's adequate for academic environments. It's completely useless for the enterprise. Packaging and installation. We'll talk a little bit about Ubuntu, but we support a tarball download, and we support, at the moment, Ubuntu in Universe, which means that if you get an Ubuntu server distribution or you get an Ubuntu desktop distribution and you add the Universe archive and you do an apt-get eucalyptus, you will get it. We also do binary releases. The only part that's binary really is the Java bytecode, but for Ubuntu as well as Debian, Lenny, and Squeeze, CentOS, and OpenSUSE. And CentOS will get you RHEL. CentOS and RHEL actually follow each other pretty carefully. We took a poll to figure out which extra distribution beyond Debian, Red Hat, and Ubuntu we should do, and the answer that came back overwhelmingly was OpenSUSE, so we did it. The Germans seemed to like it. Okay, here's a little bit about Eucalyptus Performance, and this is actually the source of, I think, a cloud myth. So one of the myths that we encountered early on was, oh no, I could never run virtualization in my data center because I'm going to lose my bandwidth, right? The VMs work great, but I'm going to lose bandwidth. And here's why I think people think that. On the left side, on the y-axis here is megabits per second. And what we did is we launched VMs 1,000 times over the course of about 3 weeks, and we just had them open a socket connection, and we measured the bandwidth. Right? On the left side are Amazon.com. The first blue dot is one availability zone, think one data center. The second blue dot is 2 availability zones, think 2 data centers probably located in Virginia. The thing that's important to understand here is that there's 95% confidence bound shown on that graph. They're obscured by the size of the dot there. small. And also, Amazon is claiming GigE, but you're getting about 480 megabits a second in a single availability zone. The right side is Eucalyptus. This is a very small machine, and one availability zone within one cluster, and then two availability zones, and that's through a layer 3 tunnel, GRE. Why? Why is there this difference? Well, the first reason there's this difference is not because Amazon is dumb. The Amazon people know how to do full layer 2 provisioning and can get you GigE if they like. This is 10 cents a CPU hour. They are undoubtedly throttling it, right? They haven't told me this, but that's such a small confidence bound, it's not a contention effect. They're just provisioning the bandwidth. And at 10 cents a CPU hour, you should be happy to get half a GigE, right? But a lot of people took a look at this. A lot of scientists uploaded stuff into AWS and benchmarked it and went, I can never run virtualization in my data center. No, you can happily run it and run at wire speeds. In fact, you can run Eucalyptus. When you're running Eucalyptus, this is with ambient load. Right? This is the Eucalyptus public cloud where other people were doing things, wire speed. Now, the other thing to understand is that the machine that generated these blue dots, these are machines that are the approximate size of North America. Right? You know, there are whole counties in Virginia that are covered with machines. That's a lot of bandwidth to do in a Virginia county. This is a tiny little machine. So if you can get this kind of performance out of something at that scale, you really know what you're doing. So the Amazon people are good. Here's round trip time. Again, 95% confidence bounds. And here you see what you would expect to see. They're doing some sort of tunneling. Our 95% confidence bounds aren't as good. That's because we're using software to do the VLANs. I'm sure Amazon is not. I don't know what they're doing. But if you do it in hardware, I imagine you get a much better confidence bound. And this confidence bound we don't really understand yet. We're using this GRE technology, and GRE and Linux don't necessarily play very well together. They do play, it does play well with FreeBSD, and so we may be able to get around some of that by playing some fancy FreeBSD tricks. But for the now, that was just standard Linux performance. This is image startup time, and it's really an inverted CDF. The way you read this is we did 100 experiments where we started a tiny little image, both in Amazon and on the Eucalyptus public cloud while people were using it. And we just sorted the reading. So the units are seconds. The green is Eucalyptus, and the red is Amazon. So the way you read this, say you go to the 0.6 and you say, okay, 60% of the image starts on Eucalyptus were 10 seconds or less, and on Amazon they were 19 seconds or less. Now, again, why is this? Well, Amazon is a much, much bigger machine, much bigger. And they're throttling the bandwidth, and they're probably using that bandwidth to launch their AMIs. They're getting actually really, really good times out of something they're at their scale. What's really interesting to us about this is the shape. These shapes are the same. Statistically speaking, that's an indication that we haven't done anything fundamentally brain dead. It doesn't mean that we can scale to Amazon speeds, and it doesn't mean that they're slow. It does mean that whatever mechanisms we are using have a generating model that's shifted, right, by their scale. That's really, really good news. And here's 4 image starts. And here we're doing multi-tenancy. We're launching multiple images on the same node, and they're not. That's the only reason that the gap changes. And you can see with multi-tenancy and shared memory, you have a different tail, which is what you'd expect. So this is just a verification that we haven't done anything inherently brain dead. This is a comparison of the Amazon EC2 tools with some tools we wrote ourselves in Python. A bunch of people were complaining about how slow the Amazon EC2 command line tools were, but they were complaining in the following way. They would say, Rich, Eucalyptus really sucks because it's slow. And so we would go in and look, and we were doing all this timing on the back end, and it didn't look slow to us. It turns out that SOAP's pretty slow. And there's a tool called Botu, and it's done by a consultant on the East Coast. It's open source, and it just exercises the REST interface. So we wrote in Python a bunch of wrappers that replace the EC2 tools line for line. They're command line compatible with EC2 tools, but they're written in Python, and they use Botu. And in some cases, they're like 300% faster. So there you go. You know, the performance in this system is not always where you look for it, and it's often easily overcome. Okay. Now what I'll do is I'll do some philosophizing. That was those are your performance numbers for the day. There's a bunch of things that we think we've learned, at least in the last year, about clouds. And just here's a few. First, the notion of private cloud, which is getting a lot of play today, is really, to us, a false notion. Yes, the CIA wants to run a private cloud. It's true. The NSA wants to run a private cloud. And there are some companies that are very, very interested in running clouds behind many, many firewalls. Mostly, though, what people want is a way to hybridize their existing IT infrastructure with what's in the public clouds. The public clouds, to the vast majority of people who are talking to us, look like a new IT resource. Not one that's going to replace all of their on-premise IT, and not one that you're going to do without entirely, but something that needs to be integrated with what's going on in your IT. And it's much easier to take something that's highly scalable and integrate it back into your IT than take something that's not scalable and integrate it out. That's what Eucalyptus is being used for there. So look for hybrid clouds as being a big deal coming forward. And in fact, 2 days ago, IBM just announced that their whole cloud strategy is a hybrid strategy, which maybe they saw these slides. In the enterprise, storage is everything. It turns out that virtualization, VMs, it's fairly commoditized. There's different formats and KVM and Xen and VMware and Hyper-V and all that stuff. It's all pretty much the same. What's not the same, particularly in the data center, are the storage architectures. Everybody does their own storage architecture. Some of them are certified, some of them are not, some of them are combining certified with not certified. You've got to keep all that stuff straight if you want to really make this available, at least in some sort of commercial capacity. And so we're working on that. Cloud federation. This is a big issue. Lots of clouds, lots of different APIs. Everybody looks at that and kind of throws up their hand and says, we need standards. And standards are not going to help. And the reason they're not going to help is because federation is a policy mediation problem. And it's only a policy mediation problem. We know how to move bits across APIs. We do. We've done this for years. And we can do it very efficiently. What we don't know how to do is take a multidimensional policy specification that's defined by one organization and a multidimensional policy specification that's defined by another organization and come up with a matching. And if you can't do it for two, you can't do it for a chain. So delegation is really, really hard. Right? If you think about the internet, the big problem that has been plaguing the internet folks for the last 30 years is which gateway, end to end, is causing me to drop packets. That's a very simple problem conceptually, but mathematically it's very, very hard. And the reason it's hard is because you have an SLA, which is more or less unspecified at each point in time. And from an endpoint, you can't tell which SLA in the chain is failing you. I asked this of Vince Cerf when he was giving a talk on cloud computing. He said, you're absolutely right. So really, policy mediation is a huge problem in this space when we start talking about federation. Why don't we have this problem today? It's because the clouds don't federate, right? They're not designed to federate. They don't have federation built into them as a first-class principle. We're going to confront this problem going forward. And then SLAs are really powerful, and what they allow you to do is build applications that are really cost-sensitive. You can tell your application what it costs to do a put. And if the application has a scheduler that knows about cost, it can make decisions about how much of your money it should spend. Should it run locally and maybe incur a wait? Or should it run remotely and pay the price? Trusting that decision is going to be difficult, but the mechanisms are there, and that's really an innovation. Clouds versus grids. So we started talking about this just a minute ago. One of the first things that we had to do is explain why what we were doing was not grid computing, and that's largely because I've done grid computing for a long time. And so here's your little clouds versus grids assertion by me. Grids have two properties that are distinct from clouds. The first property is that a grid is architected so that a single user can get all of the resources at some point. We build those systems so that a single scientist with sufficient permission can request and obtain all of the resources that NSF owns for some sufficiently important science experiment. No cloud is architected for this usage scenario. It is not possible to go to Amazon and say, give me all of your resources. It's not possible to go to Amazon and say, give me 10% of your resources. Because that's 10% opportunity cost, and for them, that's a huge number. Clouds are architected so that a large number of users can each get a small part of the cloud, right? Lots of users can buy camcorders. Lots of users can buy small pieces of your cloud. One user cannot buy all your camcorders, right? That's Amazon's model. And the problem here is that we talk about scale without units. When we talk about scale, we should say scaling in what? Scaling in resources, scaling in users, scaling in storage footprint. Nobody ever mentions that. Amazon and the cloud scale with users, grids scale with resources. Also, it turns out that it's really easy to do this illusion of infinite scale of resources if you scale with users. Why? Because you only have to predict the user growth graph. If every user is only given 20 VMs, that's the standard allocation inside Amazon, you just need to know how many new users are going to have tomorrow to know how many allocations of 20 VMs you have to add to the Amazon infrastructure for the next day. And that's a much easier prediction problem, predicting the individual gigantic resource usage of scientists. The second thing that differentiates clouds from grids is when we built the grid, and I am partially responsible for that, we engineered in the concept of federation as a first-class principle. From the word go, we asserted that all grids had to be federatable with all other grids. And this was because we're doing resource aggregation, right? This leads, though, to some very, very strange engineering requirements. For example, at one point, we actually had what seemed like a rational discussion about what certificate authority a particular virtualized Ethernet device needed to appeal to and what happens when its blacklist times out. And that's because if you're going to federate, everything that you are essentially manipulating can be federated, which means it has to be governed by a policy, which means there has to be a policy mediation engine, and all of that mechanism is associated with all of your resources. This leads to incredible complexity and failure modes that are very, very difficult to resolve, hence the complexity of the grid. The cloud people punted that. There is no federation. You just go to the cloud, you have one ingress point, and the policy is defined there, and then the rest of the cloud has to understand it. Now, it's going to be an impediment. It's an open question as to whether you can engineer federation in later on, but we can say from the grid, it's very, very difficult to do as a first principle thing. If you want to build a cloud then, which is not federated, and which scales with users, you build something that doesn't look anything like a grid, and vice versa. Clouds and grids are not the same. QED. Eucalyptus, one of the ways you can measure whether something is generating uptake is by looking at what things are using it as a platform in the ecosystem. And this is just a smattering. Again, there's something called AppScale. AppScale is an open source implementation of Google's App Engine done at UCSB by a fantastically brilliant researcher whose name is Chandra Krintz, and which spun out of our project. Early on, her group came to us and said, we want to participate. And I said, that's not a good idea. You need your own project. And I said, how about App Engine? And they said, great. And so you can actually run App Engine on top of Eucalyptus today. You say, so what? That's not something that exists in the wild. You're never going to have Amazon run Google's API and vice versa. But if you do, if you combine infrastructure as a service and platform as a service, you can write very, very interesting applications. And her group is. So that's an innovation that open source makes possible that just the public clouds can't do. RightScale. This is a company, an actual company in Santa Barbara, started by Torsten von Eichen, who some of you may know. And Torsten makes this wonderful Ruby-based programming environment or control environment, control dashboard for Amazon's AWS. Since we're AWS compatible, it works with us. We use them as our Turing test. We would tell the RightScale peoples, please point your RightScale thing at us and tell us where we break. And so that's nice. That's actually becoming part of their business model now. They're actually telling people, go get Eucalyptus and you can use RightScale on premise. We're happy for that. Cohesive FT, this just shows you how much uptake you can have, is their competitors. As soon as RightScale started doing that, they called. So we're now compatible with Cohesive FT. And RPath, this is a competitor more or less to SDSC Rocks. These guys are busy trying to applianceize Eucalyptus. We're still trying to figure out what that means, but they're very excited about it. So what this really means is that you put this stuff out there and it gets used in ways that are interesting from a research perspective and occasionally bizarre from a commercial perspective. The other part of this is Linux. Last November, the Ubuntu people called and they said, look, we think this is the next thing. We think Eucalyptus is the next Linux. And Ubuntu's mandate is to identify the next open source platform technology and to try to get it into the hands of people before the other distributions. And so they had intended really to fork us, right? They called us and they said, will you help us? And are you going to be a research project for the rest of your life? And the reason that they wanted to know the answer to that is because if the funding gets cut off and we're doing the support, they're in trouble. So we thought, oh gosh, they're going to fork us. That was really the big impetus for commercialization, right? If we are going to work with these people to make Eucalyptus available on a Linux scale, You can't do that on research grants because it's just too uncertain as to what the long-term funding is. We did a big port for them. We worked with them, and the original plan was for Eucalyptus to be available in Universe in the October release, the 9.10 release. They got so excited about it, and there was a lot of press going on, that they actually pushed the release up and delivered it April 23rd. It's actually in Universe. If you're an Ubuntu head, that's full source, but not in the main distribution. It will be in main in October, and this is Armageddon, right? October 24th, there will be 10 million downloads, north of 10 million downloads of Eucalyptus, because it just comes with Ubuntu. Right? The Debian people have contacted us. They watched all that go on. And they said, we would really like this for Squeeze. God knows how many downloads that's going to be. And we already package it for CentOS and OpenSUSE and so on and so forth. Just from our website alone, just to give you an idea, 17,000 different downloads in a one-year time period. And this is going up exponentially. So really, the uptake, and this has never happened for anything I've done before, has been, in some sense, surprising. Just to give you an idea of where we are, we started, our first release was May 28th. I actually thought of this at a meeting that I think Shava was at in North Carolina in October of 2007, and it took me till February to convince myself and then my research group that this was a good idea. Really, I didn't want to waste their time. February 28th was the first release. We commercialized a month short of a year later. We've got releases coming out. We'll probably finish off the AWS specification in the September timeframe. A lot of people ask when it is they can start contributing to Eucalyptus. We really don't take contributions into the core because we're on about a 6-week release cycle. It's just not possible to the QA for anything that we don't produce. We're going to go on to about a 6-month release cycle, no sooner than that, no faster than that in this time frame. And that way, at that point, we'll start thinking about core contributions. And as I said, the 4 Horsemen of the Apocalypse arrive on October 23rd at midnight. For those of you who might be interested in what commercialization is like, it's really fun and really scary. It's particularly scary when your customers start signing up. But really, there's this notion of scale. The units are dollars. And if you want to scale the dollars of a company, being a support-oriented company is probably not a good way to do it. That's what I'm told. So we're starting out doing some initial support and customer engagements. These are just companies that want to run Eucalyptus, and there are others that want to run Eucalyptus internally and want our help to make sure they're running it properly, to get it configured right, to tune it. From this, we are learning about products they wish to buy from us. So we will ultimately be building proprietary products that will not be part of the open source that you can then use with your open source core to do enterprise-focused cloud computing. But we will continue to maintain the open source core indefinitely. And I will conclude there by thanking the University of California, Santa Barbara. Let me say, if you're going to start a company as a professor from a university, you need the support of your department. You absolutely do. And my department has been phenomenal. Universities don't really understand software spinouts. They understand patent spinouts, but they have a hard time understanding software spinouts. Your department can really, really help. And so my department's phenomenal at that. The VGrads project, which some of you may have been associated with, which is funded by the National Science Foundation, we demoed Eucalyptus at 6 different sites, Amazon AWS, and the NSF supercomputers using the LEAD weather forecasting thing at supercomputing last year. Success. We have some new friends in the commercial sector who are eager to see what the next couple of years look like. That is my email address, and this is our website. And thank you very much for your patience. Questions? Yes, sir.
How much of your sort of company model is providing the services or sort of the software you need to actually run the cloud very well versus the open source component?
The question is, how much of the company's business model is focused on the tools necessary to run the cloud very well versus the open source? This is an ongoing debate we have with ourselves. If you're going to start an open source company, you have to try to figure out how to draw a bright line between what you're going to release as open source and what you're going to release as proprietary software. And that line moves around a lot. Here's where it is today. We will release things to open source that are generally useful. to Eucalyptus in any environment. iPhones, TinyOS, Craze, whatever it is. If it's just part of the general infrastructure and it's open source now, we'll put it out. If it is closed source, right, or it's very specifically targeting commerce, enterprise computing, then we feel like that's a proprietary product. But even there, it's gray. So one of the questions that comes up is, can you host Windows? The answer is yes. We run Windows on Eucalyptus all the time. In fact, I run Eucalyptus on my desktop. I'm not just a president, I'm also a client. And that's because I think it's a really cool desktop environment, and I run Windows. Are we going to put that out as open source? I don't know. Windows is not open source, right? Lots of people want Windows. Lots of people want to be younger. I don't know what to say about that. So, if we can make people younger, we'll put it out as open source, and we might do it anyway. Yes, sir.
So, who typically uses Eucalyptus right now, and what do they use it for?
The question is, who uses Eucalyptus, and what do they use it for? There's two answers to that question. There is the open source community, who seems to use it for all sorts of things, and they only tell us a little. And we are very, very sensitive to the notion that if you come to us on the open source side, you are not a sales lead, right? This is something that it's really hard to get the investors to understand. We have a database of IP addresses and emails from people who have volunteered to come and take the open source code, and we keep it away from the marketing guy. He wants it desperately. But you can't, right? I mean, we're open source software clients over the years. I hate it when I go to a website and I sign up my email address so that I can get a piece of software, and then I just get spammed with things trying to send. So we don't do this. So from this perspective, the sample we have is really, really inaccurate. Some people tell us what they're doing, some people don't. A lot of people who tell us what they're doing are either doing cloud computing research at a university or some research lab, or they are working on some sort of consultancy. We've had a lot of consultants call and say, I've taken Eucalyptus and I'm helping people plan their cloud strategy. Or they're building sort of on-premise platforms to homogenize their local environment with Amazon AWS. Those are the three most prevalent things that people tell us. A lot of people don't tell us, though, and one of the things that I didn't realize about this is when you do this, when you put out an open source platform that has a commercial tie like this, people get very excited about the idea that they're going to be able to take this and secretively put together something that might make them very, very wealthy. And so they won't tell you, and we don't ask. Now, on the business side, we know a lot about what people are doing, and what they're really doing is porting business logic, right? The next thing that people seem to want to run in the cloud beyond web services are really things that look like on-premise SaaS offerings. CRM, ERP, payroll, whatever, those kinds of things. Those are really multi-service kinds of stuff. And if you can make it web-based, so much the better. And Eucalyptus is a great platform for that. So the enterprise is off doing that kind of thing. Yes, sir?
Can I run Eucalyptus and then fail over to Amazon?
Question is can you run Eucalyptus and then fail over to Amazon? The answer is absolutely. As long as you're willing to pay the Amazonian charges, right? So what are the Amazonian charges? 10 cents a CPU hour. That's really cheap. 18 cents a gigabyte. If you start moving files at 18 cents a gigabyte, you can burn up some gigabytes pretty quickly. And then there's the storage cost. And I don't remember what it costs for 50 terabytes or whatever it is. But the bottom line is, as long as you know how much you're paying, yeah, it's trivial. You stand the stuff up, you get an elastic IP address from Amazon, you get an elastic IP address from Eucalyptus, and you round robin the DNS, and boom, you're gone. Yes, sir.
So one of the cool things sort of seems is I can pre-deploy on Eucalyptus and see how well it might work in sort of the Amazon implementation of their web services. And I wonder if you can comment on the fidelity with respect to that emulation. Clearly, sort of the latency was good, the bandwidth can clearly be much greater. You might not get the same answer. And going forward, are there any features of their API that might be difficult to emulate?
Yeah. Okay. The first question is how high fidelity is the emulation of Amazon? And then the second question is what features might we have trouble with that will be coming out of Amazon? Okay. So the first question, the fidelity is really good if you reject the notion of performance isolation. So Amazon gives you really no performance isolation guarantees. What I showed you is what we observe empirically, but they don't say that. And the same is true for Eucalyptus. So for example, Every VM inside both Amazon and Eucalyptus gets a private IP and a public IP. And the argument, Amazon says, you should use the private IP address to communicate between VMs within your allocation and only use the public IP address to ingress or egress the cloud. The reason is because the public IP has to do some sort of layer 3 routing, and that can be expensive. Now, in Amazon, they do it in hardware, we think, so it's really not that expensive, but for Eucalyptus, you will notice that. So you'll see a performance difference if you misuse the public IP on Eucalyptus that you won't see necessarily on Amazon, although the specs say that you can have it. That performance difference might be there. The functionality fidelity, though, is excellent. And that's because we test with programs. So you can sit down and run, the Amazon commands and do attaches and detaches and all that kind of stuff, and it will look like, Amazon. But the proof is when RightScale does it. Because RightScale has a programmatic interface, and that programmatic interface is depending on features to be precise, or it breaks. So when RightScale and Cohesive FT and AppScale and RPath and the Baltic Cloud and NASA and so on and so forth are all pounding away on this and on AWS, if they're not getting back the same answers, they tell us pretty quick. Yes, sir?
I was wondering, Dave Powers over at Lilly is a big proponent.
Yeah.
And so you've been working with him quite a while. I'm wondering if you're learning anything, perhaps from the organizational side, about what changes go on when you start to put a different type of environment together. Has that been changes, the way things are managed?
Right, we are. Dave is not our only customer, although he's a very, very good customer. We are running in Dave's data center at Lilly. And without attributing anything to Lilly or Dave, let me say this. Data centers have a variety of vintages of software and hardware in them. This is not something they talk about, but we actually know, because we work with all the Linux distributions, what the prescribed documented method is for installing Linux with and without virtualization. We have yet to encounter a data center that understands that. So Eucalyptus, what we're learning is that Eucalyptus has to be really defensive about what the installation is like in the enterprise. The good news is academic environments are 10 times worse, right? That's the good news, is, in our environment, we're not looking at machines that are 3 years old and software that's 3 years old. We're looking at machines that are 15 years old and software that spans, it's been modified and it's been downloaded from who knows where, and the local staff knows that. The other thing about academic environments is system administrators tend to be graduate students and postdocs. What's their number one job? To leave. Right? If your system administration staff takes as its number one job priority getting out of town and taking the institutional memory that is necessary to run your data center with it, your system has to be very, very defensively written. So we didn't know this, but if you can run in an academic environment around the world, you can handle the foibles of enterprise data centers. But enterprise data centers are not as well structured as their operators would lead you to believe, and we have learned that. I'm sorry, and you asked the second question, which I'll go back to, which is what features in Amazon. Let me just answer that quickly to saying we think we can do load balancing, and we think we can do the instrumentation. These are two new features that came out after January 1st, and we're only going to do things that needs to go into the cloud fabric. So SQS and SimpleDB, these things look like appliances to us. We don't really see a reason to build them in the cloud fabric themselves, and so we won't do those. Sorry. Yes, sir. Ah, yes. Will we make our own cloud? The question is, are we going to add features that are beyond Amazon? Yeah, probably. So one of the things that we've learned is from the AppScale project is that if you want to do sort of this layering, right? If you want to do platform as a service and infrastructure as a service, there's an API for credential federation that needs to be put in place. Now, we've put that in place for the AppScale people, but we haven't put it out yet. And that's because we don't really know how to test it. We're not entirely sure it's secure, right? Stefan, anywhere. So we don't want the Stefan Savages of the world mad at us. And so there's a lot that goes into actually putting something out for the crazies to get a hold of. But there are things that emerge from the experience, the open source experience, that we see people would want. And a lot of people ask us for stuff. Some of it's crazy. Some of it's not. So again, there's this question about whether, if you're AT&T and you come to me and you say, I want X, do I put that out as open source? Chances are no, right? I mean, you want it because you want to go and make money with it, and we think that's not necessarily something that the open source community needs. But, you know, there are research projects all over the world who are using it, who ask us for stuff, and we've actually put those things on our roadmap from time to time. Yeah? There's Stefan.
There's the public API that Amazon provides to customers, and then there's what they have inside
Right.
to figure out what's working,
Mhm.
what's not working, and when it's not working, how's it not working, what's the utilization looking like. Do you have anything there, or is it, it looks like it's working?
Yeah. So Stefan's question is, you know, how do you know what's going on inside your Eucalyptus cloud? And does it look anything like Amazon's? And the answer is, we do. We have we have tools that interrogate the logging that Eucalyptus generates. And you can vary that logging. This is not a good answer. It's what we use when we debug the system. And typically, when the open source community comes to us and says it's broken, we say, turn this logging on and send us the log. Or turn this logging on and send us what it is. And we have parsers. We actually have something that mines the logs for looking for certain things. So we've tried to build something that's log-based. Again, the open source community is big on logs. And so we've done it that way. For the enterprise, you need more. So we're going to release in open source as a prelude to the monitoring and metering stuff that's needed for the enterprise. We're going to release things like Nagios and Ganglia for health and status. We're going to tune up the logging stuff so that we can actually generate graphs as opposed to just log snippets. Although people are pretty happy with the logging. That shocked me, right? I didn't expect folks to be as thrilled with text logging as they seem to be, at least in the system administrator community. But this is one of those things where there's going to be some stuff in open source which is legitimate. Nagios and Ganglia, open source tools, everybody uses them. They really should be integrated with your cloud. And then there's going to be some pretty sophisticated stuff that's based on the statistical things we've done in the past, which will be more proprietary. Yes, sir?
How about user accounting?
Right. So user accounting at the moment is sort of left to the administrator in the sense that your cloud administrator for Eucalyptus is in charge of handing out user credentials and or revoking them. And that mirrors the way things are done in academic environments. There's usually a system administrator whose job it is to assign user IDs, keep track of them, this kind of thing. So all of that stuff is there. You do need a way to do capacity apportioning with respect to groups of users. We actually have the Amazon Security Group mechanism in place. So you actually can build groups of users who only have access to certain resources or SLAs. But there's a better way to do this. And we learned this from our RightScale experience. The RightScale people actually use a cluster at UCSB as a demo cluster. And what we're trying, and what we would like them to do is have like 40% of that cluster and the rights to hand out credentials to it, right, that we just don't see. So we'll get 60%, they'll get 40%. We each manage our own credentials. We don't have that quite built, but it'll be in there. And that'll be part of a whole set of proprietary administrator tools that we think are really important for the enterprise. We're done. Thank you so very much for your attention today.